Welcome to Physics 142 Online. I'd like to spend a few minutes today discussing some of the properties of resistors, especially how they behave when they're combined in different arrangements in an electrical circuit. And by doing this right now, then I'll be able to spend class time doing examples of how to use basic principles called Kirchhoff's laws to analyze the behavior of circuits. So very quickly, these topics are covered in your book, and I just want to mention some very simple properties of the resistance of a resistor. One of the things that we notice is that the resistance depends on the geometry of the sample. Not only does it depend on what the sample is made out of, but also on the geometry. And the longer the sample is, the greater the resistance is. Also, the smaller the cross-sectional area, the greater the resistance is. So there are different kinds of proportionalities here, and when we express the resistance in terms of these geometrical quantities, the length and the cross-sectional area, the constant of proportionality, rho, is the resistivity of the conductor. And the resistivity, that's a more fundamental property than resistance. Resistivity only depends on the type of material the conductor is made out of, and as we'll see in a minute, on the temperature of the material. The units of resistance being ohms, you can see easily that the units of resistivity are ohm meters. And so these are basic relationships for how to understand the way that the resistance depends on the properties of the sample. The L and the A dependence should make sense to you, because if resistance is caused by charged particles, electrons, making collisions with atoms inside the sample, well, the longer the sample is, the more collisions there are going to be, and thus the greater the resistance. And we can use the cross-sectional area. We can think of water flowing through a pipe, and when you constrict a pipe, you make it harder for the water to flow through that pipe. And the same kind of property holds true with electrons going through a conducting material. If you shrink down the cross-sectional area, the resistance to the flow increases. We can also define, some books talk, rather than talking about resistivity, they will talk about conductivity. Conductivity is simply the reciprocal of resistivity. There's not really any good reason to have two different quantities that basically are telling us the same thing, just with reciprocals, but depending on whether you want to emphasize the fact that a material is a good conductor or a bad conductor, you might want to talk about either resistivity or conductivity. And the units of conductivity then are just the reciprocal of the units of resistivity, or 1 over ohm meters. Now, I mentioned that resistivity depends on the temperature of the conductor, and if resistivity does, then resistance does as well. Also, it's not too surprising if you understand that resistance is caused by collisions between electrons and atoms, that the resistance will increase as the temperature increases, because the vibrations of the atoms inside the solid, as the temperature increases, those vibrations are more energetic. The displacement of the atoms away from their equilibrium positions is greater, and that increases the chance for electrons to collide with the atoms. There are just some very simple relationships that show that both resistivity and resistance depend linearly on the temperature. These equations, we may not use these two very much in class, but it's important to understand that there is a property called a thermal coefficient of resistivity. And that controls how much the resistance and the resistivity increase as the temperature increases. Rho 0 and R 0 are resistivity and resistance measured normally at a reference temperature, something like room temperature, and T0 is indeed that reference temperature value. Here are some representative values for the both the resistivity as well as the temperature coefficient of the resistivity for typical metals. Now, here's what I really want to do today, so that you'll be ready in class for me to do an example involving the analysis of a rather complex circuit. So let's talk about equivalent resistance. It's very similar to the concept of equivalent capacitance that we discussed when we were hooking together capacitors in series and parallel arrangements. So for resistors in a circuit that are in series, the very first thing that we can say is that if those resistors are in series with one another and then connected to a power supply, that the overall potential difference across the power supply is the sum of the potential differences across the two resistors. In a moment, we'll talk about something called Kirchhoff's voltage law, or the loop rule, which expresses this basic principle. And so, since that's true, since an electron or a current, since an electron going around the circuit has to have its energy conserved when it makes a complete loop around the circuit, we know this is true. We can also tell, for resistors in series, that the current flow through each resistor must be the same. Remember that current is charge per unit time. And so the charge per unit time that flows through resistor 1 has to equal the charge per unit time that flows through resistor 2, or else somehow charge would be disappearing. So that can't happen. There's a principle called the conservation of charge in physics. And so the way that the current flows through these resistors has to be in such a way that the current stays the same. And that means that it's also the same as the current in our equivalent circuit. The purpose of the equivalent circuit is to take into account the behavior of both R1 and R2 in one term. So if we know the first equation about the relationship between the potential differences, and we just substitute in Ohm's law, delta V is IR in the equivalent circuit, delta V1 is I1 R1, delta V2 is I2 R2 in the original circuit. So we make those substitutions, and then, since those currents, I, I1, I2, all have to be the same, those factors in the IR equation can be canceled out because I and I1 and I2 are the same. And that leaves us with a very simple relationship for the equivalent resistance of R1 and R2 in series. They're just added together. And it's useful to see as a result of that the equivalent resistance for series resistors is greater than either one of those resistors separately because they're added together. Well, what about the other arrangement? What about resistors in parallel? So here we hook up a battery to two resistors that are wired together in parallel, R1 and R2, and we'd like to know for the equivalent circuit how the equivalent resistor R would be related to R1 and R2. It's clearly not going to be just the sum, as it was in the case of series resistors. So how do we do this problem? Well, the one thing that we can say right off the bat is that the current flowing into the parallel arrangement, I, that's the current coming out of the battery, it has to go somewhere. When it reaches that node or that junction, the current flowing in, some of it will go through the upper resistor, and that's I1. Some will go through the lower resistor, but I1 plus I2 has to equal the current coming in. Current in equals net current going out. So we can say that I equals I1 plus I2. Then, if we substitute in using Ohm's law for I is equal to delta V over R. So in the equivalent circuit, I is delta V over R. In the original circuit, I1 is delta V1 over R1, and I2 is delta V2 over R2. And so then what we can do at this point is realize that when you have elements in a circuit in parallel, the potential difference across them has to be the same. And it also has to be the same as across the power supply that's connected to those two resistors. So delta V across the power supply has to be the same as delta V1 and delta V2. And realizing that, then the numerator terms in the equation above cancel out. Delta V, delta V1, and delta V2 are all the same. Canceling those out, we get this reciprocal relationship for how the equivalent resistance depends on the two resistors in parallel. 1 over R equals 1 over R1 plus 1 over R2. If I wanted to solve for R, it's not a very elegant looking equation, but if I solve for R, I get that R is R1 over R1 plus R2 times R2. And what this means, you can see that the term R1 over R1 plus R2 is always a fraction less than 1, and so therefore the equivalent resistance will always be a value that is less than either R1 or R2. And so resistors in parallel have smaller resistance overall than either one of them individually would have. So these are the two kinds of combinations of resistors that we can have in typical circuits. And so if you have two resistors back to back in a circuit, then you can combine them into a single resistor, and that simplifies the math. And the same thing holds true if you've got two or more resistors in parallel. You just combine them into a single resistor and use the reciprocal formula. Of course, if there are 3 resistors or 4 resistors, we simply add terms to the equations in the red boxes to incorporate those into the treatment. So, this gives us a very quick but simple introduction to the combinations of resistors. And now, in class, I'll go through how to use Kirchhoff's rules or Kirchhoff's laws to analyze circuit behavior. And what we usually want to do is we want to know for a particular circuit how much current flows through each branch of the circuit, and we might want to calculate how the power is dissipated in those resistive elements. Because a resistor, since it presents an obstacle to the flow of electricity, to the flow of current, it actually causes the charges that flow through it to lose some of their energy. And that energy most often manifests itself in the presence of heat. So there are power losses through resistors. Sometimes that's desirable because we might have a resistor that's simply something like a light bulb, where the energy loss is transformed into radiant energy. Or it might be a heating element in an electric heater. So the energy that's lost goes into creating heat, and that's beneficial. Other times we might not like to have so much resistance depending on our application. And so just very quickly, I'll finish off by talking about the power dissipated through a resistor and how that's related to the resistance and to the current and the potential difference. So imagine a charge delta Q that's going to flow through a resistor R from point A to point B. Its potential energy at points A and points B are simply given by the charge times the potential at that point. Okay, we've seen this equation before, and so if I want to calculate the energy that's lost when the charge moves through the resistor, that's going to be the initial energy UA minus the final energy UB. And substituting in from these two equations for the potential energy, we get delta Q times VA minus VB, or just delta Q times delta V. Delta V is the potential drop across the resistor. So what I can do with this equation, if I want to find out how much power is lost in the resistor, I realize that power is energy per unit time. So let's divide both sides of the equation by a time delta T. And when we do that, we get delta E over delta T, which is delta Q over delta T times delta V. Right here, delta Q over delta T, that's simply the current. We can take the deltas and turn them into small differential quantities and make this relationship an exact relationship. So this tells us dE dt, which is the rate of loss of energy, or the rate, or the power, basically the dissipation of power, equals the current dQ dt times the voltage across the resistor delta V. So power is just current times voltage. And this also can be used to calculate the power that's generated in a power supply. If I know that when there's 10 volts in the power supply and then connected to a particular resistor, a certain amount of current I flows, then the product of I and delta V tells me the power that's generated. So one other thing that's useful to do is to use Ohm's law to substitute in for delta V. If we have a resistive element and we know that the delta V is equal to I times the resistance, then I times R gives us I squared R. And so from the standpoint of a resistor with resistance R, if I know the current flowing through it, then I can calculate directly the power that it dissipates. So we'll use these formulas after solving circuit problems to figure out how the power is dissipated in the circuit. I will see you in class.